This is lecture 8 of the NITheCS SATACS category theory course in 2023. And we decided for today to have to try out an interactive lecture where the content that will be covered in the lecture will be guided by comments from the participants, comments, questions, and also perhaps suggestions. Would anyone like to say something as an icebreaker?
Well, recently I read about an example where one defines a circle, one-dimensional circle, as a co-equalizer of some morphisms. And I would like to discuss that fact. Can you do this general about factor objects?
Yeah, that's a good suggestion. You have seen our lecture on co-equalizers?
Yep.
Okay. So,
an example I'm talking about was from 0 simplex to 1 simplex. From point to 0, 1 interval.
Right. Yes, I can guess that. So if we take, so this is going to be happening in the category of topological spaces, but we are first going to look at a version of this in the category of sets, and then move to the category of topological spaces. So in the category of sets, let's take a singleton set as one object. So let's call this thing X. And let's take the unit interval. I'm going to draw it vertically. Here is 0, here is 1. So this is the unit interval of the real numbers. Maybe we should actually take, it doesn't really matter, but we could maybe, to make it a bit more natural, we could take this to have length 2 pi. So that the radius of our circle will be 1. And we can consider two functions from x to y, f and g. Well, since x is only a singleton, each of these functions will be determined by where x is mapped to. So let's think of f as a yellow function and g as a green function. So f then maps this point to the far end point of the unit interval to 2 pi, and g maps the same point to 0. The question is, what will be the co-equalizer of this pair of maps? And let's recall our theorem. We actually proved what co-equalizers are in general. If I have two functions, f and g, I get the co-equalizer by quotienting out y with a certain equivalence relation. Do you remember what it was? Does anyone remember what this equivalence relation was?
Well, maybe f equals to g. Something like that.
F equals g is an idea. It's not yet a relation. So yeah, indeed, we want. I mean, equivalence relation consists of ordered pairs, right? So I'm now assuming that we kind of know the content of that lecture, so I'm not going to re-explain how to arrive to this insight. And the answer here is we take the ordered pairs fx, gx, where x is an element of x. We want every value fx to become equal to gx, because we want this map Q to have the property that QF equals QG. That should happen for every x, that QF of x equals QG of x. We want this for every x. So it's natural that we would want to quotient out y by this relation, except that this relation might not be an equivalence relation. So then we generate an equivalence relation. We can write this by putting a bar across that relation. So we take the smallest equivalence relation for which fx and gx are related for every x. That was the construction we had of coequalizer in general. Now, do you want us to go into the inside of this construction, kind of recapping what we did last lecture, or do we use this and apply it in our case?
It would be nice if you like go a bit deeper.
Okay, so let's recap. Why does this construction work? Imagine I've got, I'm now going to prove that it has the universal property of the coequalizer. So imagine I have another function R that has the property that Rf equals Rg. And we want to construct this unique function here, H. Well, we can define H. So if we denote this equivalence relation by E, we can define H by setting H of equivalence class of an element. Equivalence classes of elements are what are elements of the quotient set, right? So we can define that to equal R of Y. Why do we define it that way? Well, we're kind of forced to define it that way because we want this triangle to commute, right? We want the blue triangle here to commute, and that means that a y mapping to qy will should further map by h wherever it was mapping by r. So r of y needs to equal h q of y. I keep moving these ones around. Now, what is q of y? This thing here is a quotient set, and q is the quotient map. Q of y is the equivalence class of y under E. So then I get the equality I want, that R of y needs to equal to h of equivalence class of y. But then I can use this equality to define h, hopefully. At least I see that h must be defined this way because it must satisfy the commutative triangle. But now the question is, does this formula actually define a map H? We want H to be a function, right? If it is a function, we know that the triangle will commute. We know it will be unique because we were forced to define H that way based on commutative triangle, but we still don't know if such function H exists. The problem with this formula, of course, is on the left side, we've got a parameter which could be a different one for the given equivalence class, because the equivalence class could contain many elements in it. And if I choose a different representative of the equivalence class, there is no guarantee that R of that representative will be the same as R of Y. Does that make sense, Alexandra?
Yep, it does.
Everybody else is fine as well?
Yes.
Okay, making more space here. Okay, so how are we going to confirm that the formula actually does define a function? Well, all we need to do is to check that whenever e is equivalent to, sorry, whenever y is equivalent to y prime under e, that means they're in the same equivalence class, right? Whenever that happens, we want to check that also r of y will equal r of y prime. If this is true, it will mean that this formula is independent of the choice of this parameter, because any other choice that fits the same equivalence class will be a y prime that's equivalent to e, and then by this formula, the value will be the same. Remember, a function cannot have different values for the given input. We need to have unique value. So that's what we're trying to achieve here. Okay. We'll have to unpack this. What do we know about y being related to y prime under the relation e? E is the relation generated by this relation. So now we need to, it's an equivalence relation generated by that relation. So we need to remind ourselves how that works. What's the smallest equivalence relation that contains this relation? I'm not sure if you're familiar with that construction. Are you, Alexander?
Not really. So we just take like f of y is equal to g of y, or what?
Yeah, so this is actually a very interesting construction. Let's first develop this construction for an arbitrary relation and then apply it in a specific one. It's worth talking about this because it will be needed in many other similar constructions. So how to generate an equivalence relation from a relation R. By generating, we mean to construct smallest equivalence relation that contains our given relation. Well, on the picture, it's quite easy. If I have a relation on the picture that can be displayed as a directed graph, then what we do is that we want to organize the dots in equivalence classes, which obeys the rule that whenever there is an arrow connecting two dots, these two dots must fall in the same equivalence class, right? So then it's clear that our equivalence classes will be these. Because there is an arrow here, those two dots must be in the same class, but also these two dots must be in the same class, which forces these two dots to be in the same class as well. But there is nothing that forces these dots to be in the same class as that one. And also we've got an isolated point here, which is not forced to be grouped together with any of the others. Thinking of it more algebraically, an equivalence relation needs to be reflexive, symmetric, and transitive. And so we try to turn this into a relation that's like that. First of all, we declare that this set of pairs XX, so let X be our underlying set. This is contained in R bar. This needs to take place if I want my R bar to be an equivalence relation, specifically if I want it to be reflexive. If I want it to be symmetric, then I also need every time XY is in R, I want YX to be in R as well, right? That's the property of symmetry. Now, the property of transitivity is that every time I've got a chain of related pairs, but now keep in mind that by symmetry, backwards relation is also counts as a relation. So this chain could be a chain that goes in a zigzag like that. Every time I have such a chain, let's say y1, 2, 3, 4, 5, 6, 7, y7. By transitivity and symmetry, look what's going to happen. So first of all, by reflexivity, y needs to be related to y, right? And then secondly, then because y1 is related to, let's say, y2 here, also y2 would have to be related to y1. So we kind of already covered that case here, also there for the first one. But now this arrow also reverses, and we get this chain, which by transitivity forces this arrow to be also a relation. But now by transitivity again, this one and this one here will give me another arrow, and eventually I will be able to reach all the way from y1 to y7. So I can conjecture that R bar is a set of order pairs y prime such that there exists a sequence of elements y1 up to yn, where for every index I from 1 to n minus 1, I've got that either yi plus 1 is in R, or the reverse. Or yi plus 1 yi is in R. Now, from the illustration we gave earlier, it's kind of easy to see that we are forced, at least for this to be contained in R bar, by basically applying transitivity successively. Such pairs for which this chain exists, this is basically the zigzag that we've illustrated here, will indeed force the end points of that chain to be related if my relation is an equivalence relation that contains the relation R. But then it's easy to check that this actually does constitute an equivalence relation. I'm not going to check it thoroughly. I'm just going to show you pictures that convince you of that. So first of all, we want to make sure it's a reflexive relation. Okay, why is it reflexive? Well, a pair like XX does belong to R bar. Simply consider the case when n is 0. Sorry, I forgot to add a clause here. And then I want to consider the case not n is 0, but n is 1. So I forgot to add here that the endpoints of my chain must match with my y and y prime. So y here must equal y1. So all of this together with y equaling y1, and y prime must equal yn. Does this still make sense for everyone?
Yep.
Yes.
So what happens when n is 1? Because here the set over which I ranges will be empty. That's the convention with this notation, that when you take n is 1, we get 0, and then you don't have any numbers from 1 to 0. You have numbers from 0 to 1, but not the other way around. Of course, we only talk about natural numbers here, since according to this notation, it suggests that. So then, because this is empty set, this whole clause holds automatically. And we just need to make sure that there exists these y's such that that holds and that holds. So just to put the quantifier scope correctly here. And of course they exist because when n equals 1, we can take both y1 and yn to be simply x. So that's how xx gets to be R bar. As for symmetry of this relation, that's quite easy. If you've got a zigzag, right, then you can, if you've got a zigzag in this direction, you can just reverse the same zigzag and it will go backwards. So you would just take the same sequence here, but reverse that sequence. Since we didn't care in which direction each adjacent points were related, the reversed zigzag will still work for the reversed pair. So that's how we will get that if I've got y prime in R bar, then y prime y will be in R bar as well. And finally, for transitivity, that's also not difficult. So if I've got y prime and y double prime, and I've got some zigzag here, and I've got some zigzag there, what would I do to convince myself that I also have a zigzag all the way from y to y double prime? Which zigzag would I consider? That's a question to the participants.
Well, I can just construct from definitions this frame, so this way, from these two ways.
Mm-hmm. How would you construct it? We can just put these two zigzags next to each other, right?
Yep. And just take length as a sum of lengths.
Yeah, exactly. Mm-hmm. So that's also quite intuitive. So we've got these two zigzags, we can get a longer one just by merging the two zigzags. So they do have a common point at which they meet y prime, so they can be merged. Leanne, are you okay?
Yes, sir.
Mm-hmm. Fantastic. So we've now proved that this R bar is an equivalence relation, right? R bar is an equivalence relation. Containing R. How do we know it contains R? Well, if it's just a single relation R, it means we've got a single arrow, and this is a special case of a zigzag. So that's the case where our n will be equal to 2. So R is an equivalence relation containing R. Moreover, by construction of R bar, it is easy to see that any equivalence relation containing R will be contained. So any E containing R will be contained in will contain also R bar. Now, if we think about it, imagine that we've got a relation R that contains, E that contains R. Then it means that each piece of this zigzag will be in E. But then because E is transitive, then it means that the endpoints also must give a pair inside E by successive application of transitivity, as we explained earlier. So this shows then that R bar is the smallest. By the way, this is also a certain kind of universal property. We can actually express this as a universal property in the sense of category theory. So R is the smallest equivalence relation containing R bar is the smallest equivalence relation containing the given relation R. That's what we call the equivalence relation generated by R. It's called the equivalence relation generated by R. And that's exactly what we want here. We want the Q map to map fx and gx to the same spot. But then it's clear that mapping things to the same spot itself is an equivalence relation, and we want kind of most optimal such equivalence relation because of this universal property. One needs to think a little bit about this to relate the optimalness of the equivalence relation with the universal property of Q. And so, well, I mean, here we just propose that thing, right? So we can just now prove that H is unique, H exists. In other words, we can prove this implication now based on knowing what it means for y and y prime to be related to each other by the smallest equivalence relation containing this relation. So it means we've got a zigzag, right? It means that there will be a zigzag. Now, depending on how the zigzag starts, it could be either that we've got y equals f of x1, which is then related to g of x1, and then that could equal, let's say, g of x2, which will be related in the opposite direction to f of x2, and so on. So we'll have a zigzag like this, with the direction of the arrows alternating in any random way. Here we're just giving one example. And eventually, this chain will lead up to y prime, which could accidentally be f of xn, or it could have been also g of xn. So that's what we know about y and y prime, that they're related to each other via such a zigzag, where each piece of the zigzag is an ordered pair of this form. And I want to prove that r of the y is equal to r of y prime. So I'll just put r around around the entire zigzag, basically. I'll just evaluate each thing here with an r. So make r of each of these things. Certainly, equal things will remain equal if I put r around them. But then, moreover, look at this. Here I've got r of f something, r of g something, right? But that thing is the same thing. It's x1. We know already that rf is universally equal to rg. So this arrow will become equality. R of f of x1 is indeed equal to r of g of x1. Similarly, r of g of x2 is indeed equal to r of f of x2. And so we'll have equality above every arrow once we put r around each of the nodes. Eventually, we'll get a chain of equalities, allowing us to conclude that, as we wanted, that r of y equals r of y prime. Alexander, does that make sense to you? Are you satisfied with this?
Yeah, but it's intuitive.
Fantastic. So we've now been able to remember we were proving that the formula that forces us to define H in a certain way. That formula actually does define H, and we proved that it does. So we now prove that this is indeed the coequalizer together with the quotient map Q of the pair FG. So we can apply this knowledge here. We can apply the knowledge of how to build the coequalizer to the specific diagram. So let's take this diagram and now compute what that zigzaggy thing will be for this setup. Get some more space on my board. There we are. So the coequalizer of this will be y quotiented out by the relation E, where y is related by E to y prime whenever there is a zigzag. So what zigzag are we talking about? Remember, E here will be the equivalence relation generated by the set of fx gx, where x is in x. But of course, in our case, there is only one x in x, right? Let's call this thing a star.
So it has to be like the minimal or the smallest equivalence relation that contains point 2p and 0.
That contains pair 2 pi 0. Yes.
Yeah.
So because we have only one thing in x, so the star, this will be just the equivalence relation generated by the singleton set. F of star, which is 2 pi, and g of star, which is 0. So in my zigzag, right, I will always have either this pair or its reverse. Now, if I start with this pair, 2 pi 0, and then reverse it, I can't reverse it because 0 is not equal to 2 pi. So if I start with 0 to 2 pi, then the only thing I can do is to write 2 pi here, if I'm forming a zigzag. And the only thing I can do is write 0 there, and the only thing I can do is write 2 pi here. So either we will have pairs which are of the form 2 pi 0, or 2 pi, which by reflexivity we know it's already there, 2 pi 0, or maybe like 0 to pi, right? So the only pairs in our equivalence relation will be the pairs xx, where x is any element in the interval from 0 to 2 pi, so that's guaranteed by reflexivity, together with just a few others, which will be obtained by these zigzags. But as we investigated now, the zigzags can only give pairs of the form 0 to pi or of the form 2 pi 0. So what does that mean in terms of our quotient set? What are the equivalence classes? So from here, every x is just related to itself. So these are singleton equivalence classes, unless the number is either 0 to pi, in which case they fall in the same equivalence class. So basically what we get here is that the 2 pi and the 0 now must belong to the same equivalence class, but everything else stays as a singleton equivalence class. Of course, these circles are infinitely small. Geometrically, the geometric intuition of a quotient set is, of course, is that we things that belong to the same equivalence class, we think of it as being glued to each other. So geometric intuition of this is indeed that we take these 2 points and we eventually glue them together. Hence, we get a circle. Does that make sense? But we only get a circle set theoretically, and we also want to do this topologically. Now, are you familiar with topology, Alexander? Do you know what a topological space is?
Yeah, I have attended Anzori's lecture, so yep.
Okay. And Lian, you're also comfortable with that, right?
Yes, sir.
Yeah. I'm not asking you, Brandon, because I'm sure you know what a topological space is. So it turns out that the coequalizer in the category of topological spaces can be constructed in a similar way. I'm only going to give an outline. We're not going to enter into details. So firstly, we need to agree on what kind of topology do we have on X and on Y. And then using that, we can make a guess, and then eventually one can prove what will be the topology on the quotient set. So the topology on the singleton, there is only one topology on the singleton. Topological space has a bunch of open sets, and the entire set, the empty set, must always be open. And so, but that covers all possible subsets of this. So everything is open here, which means the empty set and the singleton of and the unique singleton, the one containing the star. The topology on the interval that we borrow from the real line topology. So the interval is a subset of the real line. And if you take a topological space, you take any subset. By restricting your open sets to that subset, you get a topology. It's called induced topology on that subset. It's also called subspace topology. Typical open sets will be open intervals, their unions, but also intervals of this form, which are open on one side, and the other side, they contain the boundary of the interval. That's because we get them by intersecting an open interval from the real line to that subset. So these are the open sets in that topology. The things I drew and their unions. Their intersections will also be of that kind. So we just need to take their unions. And also infinite unions are allowed. So for example, this would be one such thing. So I've got all these sets, all those sets. The boundaries are not included. So that will be an open set, and all open sets will kind of look like this. With possibly also infinitely many fragments, not just finite. Okay, and then we need to figure out what the topology here will be, and then that can be done using a general construction. So let's consider topological spaces x tau and x prime tau prime. And let's take two continuous functions, f and g. Continuous functions means that the inverse image of open is open. And we consider the coequalizer of f and g in the category of sets. So in the category of sets. And we want to put a certain topology here, tau double prime, that will make this also a coequalizer in the category of topological spaces. So we can actually kind of guess what this should be. Firstly, whatever it is, whatever tau prime is, we want Q, the quotient map, to be continuous, right? So we definitely know that if I take any open set in tau double prime, I definitely know that Q minus 1 of that must be inside tau prime. So that kind of gives me a limitation as to what kind of things can be open in the coequalizer. How is the limitation? Well, I'm only allowed those O's to declare to be open whose inverse image is open in tau prime. Now, pictorially, what does this mean? So you've got this X, right? And remember, the X has been now partitioned into equivalence classes. And the set we've got on the right-hand side is the set of equivalence classes. So now I'm picking some random O here and deciding whether that needs to be open or not. But if I, by chance, decided it must be open, then because Q must be continuous, its inverse image must be open in space X. Its inverse image has a nice drawing. Inverse image of each point is the entire equivalence class. So its inverse image will be the union of these equivalence blocks or equivalence classes. So inverse image will be, in this case, will be this area here. So only these kinds of sets on the right side, for which the blue area on the left side is open in X, are allowed to be open in the coequalizer. Now the question is, do we allow all of them actually to be open? Do we declare that any such set must be open, or do we maybe decide that none of them should be open? The thing is that if I do decide for anything of that kind to be open, Q will still be continuous, right? So if I take my coequalizer in set of f and g, and I take as my open sets, let's call this thing tau prime tilde, as all those blue sets for which the inverse image, that union of blocks, is open in tau prime. So in other words, tau prime consists exactly, tau prime tilde consists exactly of all the subsets O of the coequalizer, such that Q minus 1 of O is open, then this map Q will still be continuous. And by our universal property, there must be a unique map here. But of course, the maps Q here are the same map, right? And the triangle must be commutative, and these maps are surjective also. So it's kind of obvious that this must then be identity map of that coequalizer. That unique map must be identity map. But if it's identity map, then anything that's open here, its inverse image along the identity map, which will be the same set, must also be open here, right? So that forces anything that's in here also to be in there. And remember, this was the biggest that tau prime could have been. But now we also know that tau prime has contained it. So we have two inequalities. First of all, tau double prime must be inside here. That's our limitation on what the open sets could have been. But now by continuity of this map, it turns out that tau 1 double prime must also be contained in tau double prime, hence giving that actually tau double prime must equal to this thing. And so that's the general description of a coequalizer in the category of topological spaces. One can then prove that that this conjecture we came up with, that this thing must be a coequalizer, actually is a coequalizer. So you take the usual coequalizer. Sorry, yeah?
As far as I have understand, we just take coequalizer in sense of sets that you have just described, and make topology to be in those topology with that Q that we have from coequalizers as in sets, right?
Yes, yes. By induced, we mean that anything on this side is open, if and only if its inverse image under Q is open here.
Yep.
So that's how we can then get a topology on the circle by this construction. And then it turns out that the topology we will get this way on the coequalizer on the circle will be the same topology we will get on the circle if I was thinking of the circle as a subspace of the Cartesian plane. When we think of a circle as a topological space, the typical thing to do is to think of it as maybe the algebraic thing to do is to think of it as a subspace of the Cartesian plane and induce topology from the Cartesian plane. And that topology will turn out to be equal to the topology obtained on the coequalizer through the construction we just gave. And so that's the piece that would have to be proved in order for us to get convinced that this coequalizer is indeed a circle. The fact that these topologies are the same. It's kind of not so difficult to see they're the same. So what are the topologies on the circle induced from the Cartesian plane? Well, on the Cartesian plane, basic open sets are open disks. So if you overlap an open disk with a circle, you get an open interval kind of lying on the circle, right? So the topology on the circle is the one that's generated by these open intervals on the circle. Basically, these are they're arbitrary unions because intersection of any two such things is still such. What about the quotient topology here? In order for something to be open here, its inverse image must be open there. What kind of inverse images do we get? I mean, if I take something like this, right? Let me use a different color. If I take something like this, its inverse image is going to be this, which we know is open on the interval. On the other hand, if I take something like this, its inverse image is this together with that, which is still open. And so you see the shape of these basic open sets will be same in both cases, hence the topologies are the same. At least intuitively, does that make sense, Alexandra?
Yes, it does.
But of course, to write everything out formally, one would have to do a bit of writing.
Yep.
The important part here is that we can never, I mean, so here we had these weird things where there was closed on one side, kind of. We'll never encounter that here because every time I've got something like that, because this point is there, now to the same point also something from there is mapped. So everything of that kind will definitely have to be coupled with something on the other side. Just because this thing on its own without that part is not open. So this weirdness we had on here, right, that will eliminate once we do the co-equalizer. And in fact, these two pieces give the desired intervals which cross that gluing point. Okay, so that was kind of answering the request you gave us, and thank you very much for that request, because we ended up touching on very important topics. Now the question is, what do we do next? I'm waiting for some suggestions from you, from any one of you.
Would it be possible to take this one step further and maybe create a cylinder with the co-equalizer and an interval in a square?
Yes, it would be. Thanks for that question. So let's make a sketch of that. I could take a square. Maybe let me take a rectangle. Actually, no, I want it the other way around, right? Because I want to then turn it around. And I could take a single interval, and I can have two maps. Maybe I'll draw it a bit skewed. I'll have two maps. One of them will be embedding this interval onto the left edge of the rectangle. The other map, we use the green color or the blue color, but let's use the green like before. The other map will be embedded here on the other edge. Now, when I take a co-equalizer of this, every time I pick an x here, it creates fx and gx. So there's f map, there's g map, and we know that this fx and g map must stick together. And in fact, that will be the only ones that stick together. In our zigzags, again, the zigzags will have a trivial form. So let's kind of formalize why. The two maps here, of course, if I describe my rectangle as, let's say, I've got my unit interval times the interval 0 to pi. And I've got unit interval here, and I've got two maps, f and g. And so the f map is defined by mapping x to the pair x0. The g map is defined by mapping x to the pair x 2 pi, right? You agree with that, Lian?
Yes, sir.
Now let's see what kind of things, what kind of zigzags do we get? So basically,
wouldn't it be like vice versa? 0x and 2 pi x, or?
well, I mean, look how I describe it. Yeah, you're actually right. So my coordinate system is flipped. Thanks. So this is what I meant there.
Oh, okay. All right.
So x0 gets related to x2 pi, right? But then if I want something backwards here or even forward, right? Okay, there could be another x prime, but then here it should be 2 pi or 0. It must be 2 pi to match with this pair, but then x prime must also match with x. So this something that goes in backwards, let's say, right, would have to have again x2 pi, and then here we're then forced again with x0. So throughout the zigzag, we will always have x in the first. If I started with x, we will always have x in the first coordinate, and the second coordinate will either be 0 or 2 pi. So that is to say that the equivalence classes will be just these paired together, and that's one equivalence class, and another one is these paired together, and so on. And then, of course, the effect of quotienting out by that relation will be that we take our cylinder, we take our rectangle and we turn it into a cylinder by gluing these. So that's the coequalizer, again in the category of sets, and for topological spaces we would have open sets here to be those which by inverse image give open sets there. And once again, this turns out to be the same topology as if I had induced my topology from R cubed by representing a cylinder as a subspace of R cubed, which would require a proof, and of course that proof would require first parametric representation of the cylinder. And the same applies not just to the cylinder or Möbius band and declined bottle and all these interesting geometric shapes, which parametrically can be very difficult to represent. But now we don't need to anymore. We can construct them, these topological spaces, just as colimits. And to describe a colimit, you just describe the diagram. And as you see, the description of the diagram very intuitively corresponds to how you build that space in your imagination by gluing things, and twisting things, and so on. We did touch on a bit of on this intuition in one of the other lectures. Leanne, are you satisfied?
Yes, sir.
Are you sure? Maybe you want us to fill any gaps that are left?
Oh, no, sir. It's fine.
Okay. Then I'm waiting for the next request. Next question or request or suggestion.
So,
sorry, you go first.
No, it's all right.
Zurab, have we spoken about natural transformations yet?
No, we haven't.
Can we, or not yet?
Yeah, we can. Sure, we can do that. Maybe let's see. Maybe Alexander's question was quicker because that will fill up the rest of the time. What did you want to ask, Alexander?
So I'm interested about natural transformations as well, but my question was about, like, can we generalize these things about circles? So how can one describe circles of higher dimensions, degrees?
Yeah, you can. So let's go one dimension higher. A sphere. How can we get a sphere? Take a rectangle and stick all these points on the edge with each other. So exactly how in Georgia we make khinkali, huh?
Yes, it's nice explanations.
So eventually you'll get something like this. Khinkali is a traditional Georgian food that illustrates nicely this construction. And you eventually squeeze this to the point where it becomes a single point, and then you kind of reshape the whole thing so that it becomes a circle. We don't do this step in Georgian cooking. We only leave it up to here. So here we'll have it a single point. And if you want now to go one more dimension, I've never thought of that, but I would imagine that I would expect, but since I've never thought, I have to be cautious, that we take a three-dimensional block and we glue its boundaries together. So here, look what we did. We took a two-dimensional. So for the circle, we took a one-dimensional block, right? And we glued the boundaries together to get a circle.
So what would be like f and g functions for which we construct this coequalizer?
That's a good question. So here, yeah, that's actually a good question. So because I think there it was, the representation was more elegant because we just had these 2 points. Here, we would need to have this boundary embedded. That's one function, f. So that just embeds the boundary. And G would probably have to be mapping all the points on the boundary to just a single point. So that's what G will do.
Yep, that makes sense.
It's a bit less elegant, maybe, or less symmetric, rather, than the other construction. I think this is the best I can think of at the moment. Maybe there is a more beautiful one, but at the moment it feels like this is the best we can do. And then for the next dimension, we would probably take a three-dimensional cube and squash its boundary to a single point. But I'm not so confident about that because I haven't thought about this, and one will have to carefully think whether the generalization will be so straightforward or not. I mean, it feels like it should be that, because here with one dimension it's just the boundary of the interval, and the two dimensions it's the boundary of the rectangle. It kind of feels like with three dimensions that's what it will be, but I stand under correction. It's actually it will be an interesting assignment to prove that theorem for the next dimension, maybe for all the dimensions. Shall we look at natural transformations, or would you like to do something else? Brandon, shall we embark on the natural transformation journey? It will probably take the rest of our time. Okay, great. Let's do that. So then what we're going to talk about now will kind of nicely link with our the first part of our last lecture. Was it last lecture or on before, where we defined functors? I don't recall now. One of those lectures. And maybe since we were talking about topology, maybe we can motivate it from topology. There is a notion of homotopy in topology. So in topology, you've got continuous maps, but you also have something happening between continuous maps. In our example of the unit interval and the two maps, F mapping point at one endpoint and G mapping it at the other, we can observe that the point to which X is mapped to by F and the point to which X is mapped to by G, these 2 points are not so far from each other. In fact, in this space, we can move from one point to another. There's a path that can take us from one value to another value. And that concept turns out to be very important in topology, because sometimes when there is such a path, you want to even stick points to each other if they can be connected with a path. And this way, understand how your space splits up into separate pieces. If my space, for instance, was just a disjoint union of 2 disks, this time containing the inside of the disk, I wouldn't be able to move from one point here to another point there in a continuous way. There's no continuous way to move. I'll have to go here, and then I'll have to make a jump, and then go there. Whereas here, there is a continuous way I can move. Now, we are not going to talk about homotopy today. So this was just as a way to link natural transformations with the pictures we had before. But now when we move to category theory, we can think of a category as a kind of a space where the points of the space are the objects, and the morphisms are paths that you can take to move from one object to another. And think of it kind of transformations of objects. And when I have two functors, f and g, I often want to link those two functors as a way of passage from one functor to the other. I can call this map, or this morphism, nx. Sorry, this thing should be here, g of x. Okay, so what's the setup here? Now we've got two categories. One category is right here. Let's say the category x. And then we've got another category. Let's say the category c. And we've got two functors from x to c, f and g. And we're defining a way to transform from one functor for another functor. We will call it n. And as a mathematical data, it simply consists of the family of maps, of the nx maps, one for each object x. So that's all it is. As a structure, I still have to say what conditions it needs to satisfy. So for every x, one nx is specified. Now, imagine I've got a morphism from x to y, f. The functor f will map this morphism to a morphism. The functor g will also map that morphism to a morphism.
So f is some morphism from x to y here?
Yes, in the category x. And we can get this diagram by drawing the values of the functors f and g on this morphism, and also drawing the nx and the ny component of the data n. Now, of course, if I'm thinking intuitively about transforming one object into another, one functor into another, then this transformation should also interact somehow with what the functors do for morphism. It shouldn't just be about objects, right? Because functors is not just about objects. It's something that deals with objects and morphisms. And moreover, intuitively, I want this transformation to be natural. And what does that mean? I want it to give me a way to transition from one functor to another, which takes into account how functors act on morphisms. And that means the following. So I'm just giving like an intuition, right? So there's nothing really you can hold on for now to agree with me that the intuition will be implemented correctly, but I'll tell you how the intuition is implemented nevertheless. If I move from fx to fy by ff, right? If I transform from here to there by ff, and then I apply the transformation ny, I want that result to be the same as if first I did nx and then transformed. So basically, I want this square to commute, and I want that for every f. And the intuition there is that it shouldn't matter when do I move from one functor to another, immediately, or first I move around between objects to another one, and then I transport to the other functor. So it should make a difference. And so the condition then says that for every morphism f between any two objects, in the category X, I want it to be true that ny composed with f of f equals g of y composed with nx. We're now going to give examples to illustrate this concept. And then hopefully you will see from the example that indeed this makes the transformation natural. Our first example will actually be coming from one of the previous lectures where we talked about generalized elements. But let me first write this definition up. A natural transformation n from a functor f to a functor g is a family of morphisms in the category C, where C is the codomain of the two functors. Such that this property that I wrote here holds, this one. Okay. So let's consider the generalized element functors. And if you recall, we were assigning to every x cx, and that was a functor. That was a functor from the category in question, let's say category, for similarity of notation, let this be the category X, to the category set. And that functor depended on a choice of object C, right? But now what if we have another C? Let's say D. This would give us another functor from dx, right? And remember, we think of this as a set of generalized elements of X based at C, because these generalized elements will be arrows from C to X whose domain is C, whereas this will be the set of generalized elements of X based at D. And we want to introduce change of base transformation for these sets of generalized elements. For if you have a generalized element X, right, based at C, and if by chance you have a fixed arrow, let's call this arrow alpha from D to C, then by composition, I can get a generalized element X alpha. So it's a way to change the base of a generalized element. It will actually turn out to be a very, very useful construction. Remember, the whole philosophy of generalized elements is that it can be convenient to think of my object in a category as a set, but this thinking depends on the choice of the base. Eventually, I want to be able to move between bases also, because eventually I actually want to talk about arbitrary bases, and if I want to talk about arbitrary bases, I expect that I would want to move between bases, and indeed we will want to do that, and that to be explained later. So what will this alpha do for us? Then it will allow us to move from hom CX to hom DX by mapping every x to the composite x alpha. So just as before, we have two functors, the f functor, fx equals hom cx, and the g functor, I think the colors have swapped now, gx equals hom dx functor. And now here I seem to be defining transformation nx. Remember how when we think of objects as generalized sets, I want to simultaneously think of morphisms between objects as functions between those sets. And remember how this is achievable. So we'll have hom cy here, and we have this function hom cf, which simply takes a generalized element x, and evaluating this function at x is just composing fx. But now the green base, the base d, also allows me to view f as a function. With its own hom df. But at the same time, once I end up in my codomain y, in elements base c, but elements of y, I mean generalized elements of y, I can again transform here. I can map anything from here, specifically fx, can be mapped to fx composed with alpha. And now, naturality of this transformation tells me that if I take my element, right, I switch its base and then evaluate by the f function. It should be the same as first evaluating by the f function and then switching the base. So the change of base doesn't mind when we evaluate the functions. So morphisms now being represented as functions. When their values are computed, it doesn't matter whether we first compute the value and then change base, or if we first change base and then compute the value of f at that element. And if this is so, it will be very convenient, right? Because then we don't have to worry about when do we change base. We can change base whenever we need to. We don't have to have a fixed point when we change base. We can first apply a lot of functions, f1, f2, and so on, and then change base. Brendan, when I'm talking, does it make sense? Because it's a bit too abstract at this point, so wondering if it intuitively makes sense.
I'm happy so far.
Okay, and now we can get convinced that this diagram indeed commutes. So if I take x, here it maps to fx, and it down here will map to fx alpha. On the other hand, if I first map down, it maps to x alpha, and then by hom df, it will map to f composed with x alpha. But of course, by associativity of composition, these are the same. So we get that we've now established that the transformation n given by the family of nx's from hom cx to hom dx, where x is an element of c. Is it a c? Sorry, no, it's an x. Is a natural
So it's a natural transformation of these two functors from our category X to category of sets? Or
yes,
okay.
exactly. So we can call this natural transformation. This is not a standard terminology, by the way. I made it up just now. We call this natural transformation change of base transformation for generalized elements. Let me show you another example of a natural transformation. This one will be very useful for us later on. Let's take the category of sets. And let's take two functors from the category of sets to the category of sets. One will be the identity functor, so mapping everything to itself. And the other will be the power set functor, mapping a set to its power set. So how does that work? X. Okay, let me see if my colors. Yeah, I already switched my colorings, right? So it doesn't matter which one I do. So an object X is mapped to by this functor. Let me actually describe it on the side. So X is mapped to the power set of X. We all know what it is, the set of subsets of X, right? It's all the S's such that S is a subset of X. And I just need to describe what it does on morphisms. If I've got a function f from X to Y, then I get a morphism here, which we can call P of F. And that will, what do you think it will do to a subset S? Where should I map a subset S so that I get a subset of Y, and that's obtained by F?
An image of,
yeah, which we usually write F of S. So it's all the F X's where X belongs to S. This is a functor. It turns out it's a functor. It's not difficult to see it's a functor. Preservation of composition and identity morphism is quite obvious to check that. So we get this functor, which we call the power set functor for now. There is also another power set functor with the inverse images, which will go to the opposite category, but we now work with this one. And yeah, let me call this thing here P. And we're now going to build a natural transformation from, we're going to build a transformation from identity functor to the power set functor. Now, in nature, natural transformations arise by observing that there is a kind of natural way of relating the values of one functor with the value of the other functor, something that works for every X. And then if it is really natural in the sense that you feel like this should work for every X in a kind of uniform way, that's when you usually end up with identifying a natural transformation in the sense of category theory. So in this case, if I take X and I map it by the power set functor, I get the power set of X. If I map it by the identity functor, I get the same X, right? So this is the identity functor applied to X. Can you think of a natural map? Now, by natural, for now, I mean natural in the intuitive sense, a natural map from X to power set of X. Where would I naturally map small x to?
Just to a set consisting of exactly one element?
Yep.
X?
Yeah, that would be a very natural thing to do. Okay, let's call this thing NX. Now, it turns out this NX is a natural transformation in the sense of category theory. Okay, let's check that. So what if I have now F from X to Y? This will give me at the level of power sets, will give me this Px, Py, and the function that maps every S to the image, right? Here I have Y. Here I have this map that maps every small y to the singleton Y. And here I have just the same f, because that was the identity functor, right? So for this transformation, for this family of maps nx to be natural, it now means that each of these rectangles must commute. So in our case, this nx is the family, sorry, n is the family of functions from x to power set of x, given as we described earlier. Okay, let's check if it commutes. I pick an x, I move up, it goes to singleton x. What's the direct image of the singleton under f? Well, it's of course singleton of fx, right? Okay, but now if I go right, I get fx. And where does it get mapped to by ny? It maps to that singleton of fx. There we go. It's a natural transformation. Brandon, are you happy with that?
Yes, thank you.
Leanne, were you able to follow this example?
Yes, sir. I think so.
There are lots of natural transformations in the world. Here's another one.
So can you maybe like
Yeah.
explain the reason why you mentioned homotopy theory here? Is it some type of natural transformation as well? Or?
Yeah. You know a bit about homotopies, don't you, Alexander?
Yep.
Yeah. So homotopies are arrows between continuous functions, right?
Right.
And natural transformations are arrows between functors. So in both cases, we've got arrows between arrows.
Ah, all right.
And then there is an abstract approach to this story, a two-dimensional category, where you've got arrows between arrows. You formalize that concept. And you can even have arrows between arrows between arrows, because you can have higher degrees of homotopies. And eventually this leads to unification of homotopy theory and category theory, where you deal with this nesting of arrows between arrows and between arrows. And a lot of things can be done uniformly that is applicable to categories as well as to topology.
All right.
So intuitively, we can indeed think of a homotopy between continuous functions as a natural transformation. Okay.
You can transform a functor into itself, right, with just a family of identities.
Yeah, there is always the identity natural transformation. That's a good point, yes. In fact, since you mentioned that, given two categories, X and C, I could consider functors from X to C, and that's a fun thing to do, where objects are functors and morphisms are natural transformations. And it turns out that we can compose natural transformations. That's quite easy. We can compose them component-wise. This is a category. So objects are functors from X to C, while morphisms are natural transformations. How do we compose them? Well, remember N is the family of maps from Fx to Gx. And M is the family of maps from Gx to Hx. This should be X, sorry, not C. And I think just at this level, it's quite obvious to see how we can compose them. M composed with N will be the family of maps Mx composed with Nx for each X. It will run from Fx to Hx, won't it? So that means that just like with sets, where we can do exponentiation of sets, remember a good notion of exponentiation of sets is where we take the set of functions from y to x. F is a function. This generalizes exponentiation of numbers because if this cardinality is n and cardinality is m, the number of functions from m element set to the n element set will be exactly n to the power m. So just like we can do exponentiation of sets, now it turns out we can also exponentiate categories, where this exponential is defined as the category of functors from x to c. We will come back to natural transformations quite a few times for the rest of the course. We will use them very nicely for getting an even better insight to generalized elements, something that was already hinted on in the example I discussed right here. In fact, what we will do, just a quick synopsis of what we will do, now that we learned about exponentiation, we will see if I can make this bigger. If I can't. Okay. Then I'll make it bigger here. We will take a category X, right? And we will consider set to the power X up. So what I'm going to say now will be a bit abstract and vague, but it's just a synopsis of what's to come. So we take category X, we take this functor category from the opposite category of X to the category of sets. And then it turns out that, remember how we were thinking of every object in the category as a generalized set by this functor hom CX? Now it turns out that I can view that as a process of mapping object X to the functor hom dash X, where it's the base of generalized elements now that's variable. Previously, with previous functors, we had the base fixed. The base was fixed, and it was the object that was variable. The object is still variable in this process from here to there, but for a given x, I now have the entire collection of all the bases together by turning that into a functor in the first variable here. And this allows me to embed it will turn out that this is an embedding in a suitable sense, an embedding of the category into that category. It's, by the way, called Yoneda embedding. And the purpose of this is that this category turns out to behave almost the same way as the category of sets. We can work with elements here just like we can work here. And so this whole story of generalized elements now reduces to simply taking my category and embedding it to one which is very similar to the category of sets. Moreover, this embedding will preserve limits. So if I want to work with limits here, I just embed it here, I embed my category here, and then work with limits there. And then working with the limits there is the same as working with limits in sets. And so this technique of generalized elements is actually derived from the embedding. But we will not go into too much detail here. We will come back to this at a different lecture. By the way, talking about homotopy theory, a friend of mine, Irakli Pachkoria, who is a mathematician working in UK at the moment, he tells me that Yoneda embedding is used quite a lot in homotopy theory, at least in modern homotopy theory. I think we have time still for one more request.
So you just mentioned like I don't know if I saw it correctly, but some exponential of objects maybe. Can you like explain what does exponential look general in a category? Because I know like that there's some special type of categories called topos, where there's like a request to be an exponent.
Yeah. So yeah, I can. And to explain that, we will again need to use natural transformation, as it turns out. So if I've got a category C, by the way, Brandon, what I'm explaining now also is very relevant to logic, because that's how we get implication in logic. And I think you also work with exponentials in your work, right?
Yeah, we call them valuations, but they're the same thing.
Yeah. So I've got a category C, and I fix an object X in it. I could consider this functor from C to C that that takes Cartesian product with X. So C is mapped to X cross C. And I can call this the functor F. Let me call this the functor F. Then I will want to have a functor that kind of goes backwards, but in this case, it doesn't matter what the direction is, because on both sides we've got C. But I want to think of it as going backwards. That will take my object D and will produce something that will be called D to the power X, so the exponent. And this entity is defined via a suitable natural transformation. So it is the kind of functor, so this exponentiation functor is the kind of functor that will satisfy the following condition. If I take Hom X cross C D, I want that Hom set to be bijective to the Hom set C D to the power X. That's not all I want. This is just one thing I want. Actually, I'm going to display this bijection vertically, because it will turn out to be a natural transformation. I want to have these bijections. I will call these bijections phi, and they are indexed by C and D, by two parameters. X is also present there, of course. Remember, X was fixed, so I'm going to put X as a superscript of phi. It's not an exponent at all, it's just a superscript of phi. So by drawing this phi, which I want to be a bijection, I'm actually building here a natural transformation. And so let's specify what the functors are. So you see there are two parameters, C and D. So I could think of this as having the Cartesian product of the category C with itself, where the parameters C and D come from. So ordered pair CD. Now this category is just the category whose objects are ordered pairs of objects, and morphisms are just ordered pairs of morphisms in each coordinate. So it's nothing unusual. But I want to invert one of these categories, okay? Then I apply the two functors, taking me back again to C op cross C. One is multiplying by X functor, right? And then in the other coordinate, I just keep the identity functor of C. So basically, a pair CD by this functor will be mapped to the pair X cross C D. And then I apply the home functor. So the home actually turns out to be a functor from C op cross C to the category of sets. Again, this is something that we are going to not go into much detail right now. You can kind of confirm yourself how home is a functor. But we could have also gone the other way around. So we could have first applied the functor identity of C op cross this exponentiation, which would have mapped the pair CD to the pair C d to the power x. But remember, d to the power x is not defined yet, right? So I'm only, for now, I'm just assuming I've got some abstract functor g, whose values I'm denoting like this. So we will put a condition on that functor, and then that will define the functor. For now, it's just any given functor. And then I can compose again this thing with home. As a result, I get two functors from this category to set. One is this top composite, and the other is the bottom composite. And now the phi maps give me a transformation from one to the other. So we've got a fixed x, so this is phi x. And now you see why it's indexed by the pair CD, because a natural transformation should be indexed by the objects of the domain, and the objects of domain are pairs. So that's how the components of this transformation end up being indexed by C and D. I want two conditions to hold. I want each phi to be a bijection. And I also want the following diagram to commute. And this diagram will actually be nothing other than a naturality of phi. The fact that phi is a natural transformation. I put C prime here, I put D prime to the power x. Home x cross C prime, D prime. Here I have phi x with C prime and D prime. And what have I got horizontally? The value of these two functors. Remember, this was the functor f. Do I have f somewhere else? No, we already have f there, so I don't want to call it f. Let me call this L and R. So this is the value of L at some pair of morphisms in this category, which is a pair of morphisms in each coordinate. But remember, the first one is a flipped category. It's the opposite category, right? So the first morphism will run in the opposite way to the second one. So it's L of some fg, and here is R of some fg. And what these L and R do is the following. So first of all, I need to write what f and g are. So this will be the second condition, actually. Sorry, just one moment. I'm back. So for each f that now runs from C prime to C, so it's a morphism in C. In C op, it will be morphism from C to C prime. And G that runs from D to D prime, again in C. this diagram that I'm drawing now commutes. And so let's explore what it means for it to commute. If I take an element of this Hom set here, which will be a morphism from X cross C to D, right? If I map it down, I'm going to get phi of X. I'm not going to put all these superscripts and subscripts for phi just to keep the notation a bit neater. I'm going to get phi of X that will be from C to D to the power X. Okay, then I map to the right side. Then I map this to whatever that thing will do to it. And remember that F is a morphism from C prime to C, so I have something going in here from C prime. On the other hand, G is from D to D prime, and because this thing is a functor, I've got a corresponding morphism D to the power small g going from there to D prime X. And I'm simply going to compose this phi X on one side with that F and on the other side with that. So that will give me the composite phi X with F and with D to the power G. So that's chasing the diagram along this side. Now, what about the other side? There, it will be a similar composite. So imagine I've got here X cross C prime, and I've got here D prime, and I've got my G, and I've got here identity cross F. Remember, F was from C prime to C, and identity cross F is just the morphism induced by the universal property of the product, which comes from first coordinate not changing it, keeping it with identity, and the second coordinate applying F to it. We didn't quite talk about this, I think, but hopefully it's still intuitive what this should be. So we'll just compose X with those things. We will then get X composed with identity of X cross F, and further on the other side composed with G. Maybe I shouldn't write the composite symbol because I didn't do the other side. And of course, this will be mapped to, I want this to be mapped to there, and that will be mapped to wherever phi it will take it, right? So I can now write down this equation. Phi of X C prime D prime applied to Gx identity of X cross F must equal D to the power G phi of X F. So this is the equation that represents that this square commutes, and of course this square commuting itself represents the fact that the phi family is a natural transformation from the yellow functor to the green functor. And then it will turn out that when such functor G exists, the one for which we have a system of bijections for which these squares always commute. If such G exists, then such G will be unique up to natural isomorphism. So if there's another G, they'll be connected with a natural transformation that such that each of them is an isomorphism, each of the components. Just like here, this is a natural isomorphism because each component of it is a bijection. And then that will be called the exponentiation. Now, all of this feels a bit complex, and there is a reason for that, because we skipped over an intermediate notion, the notion of a junction. This F and the G here they form an adjunction, and all the things we said about them was basically to specialize the general concept of an adjunction to this special case. So that's what an adjunction in general is. An adjunction, sorry, so the adjunction between two arbitrary functors F and G in general is what you get by declaring that you've got these kinds of bijections satisfying these diagrams. We will come back to the notion of a junction later on. It's a very important notion. In a sense, you only start to understand category theory when you understand the concept of a junction. I just still wanted to, without having done that notion, kind of give a bit of a glimpse of what exponentiation is. But maybe what we can do now, for the remaining time, is to confirm that all these conditions do hold and simplify quite nicely in the case of usual exponentiation of sets, which is the taking the category of, sorry, they're taking the set of functions. So let's unpack what this diagram is all about when we are working with the category of sets. Before I do that, do you have any questions, Alexandria, on the theoretical part of my explanation?
It's a bit confusing, but it's all right.
Maybe we can make it a bit less confusing. So I wanted to kind of show the bigger picture. So maybe you have some questions on fine-tuning the bigger picture. What is what here?
So maybe you could like explain what it would look like in a category of sets.
Yeah, that's what I said now. Okay, then I'm going to do that. Okay. So in the category of sets, by d to the power x, we mean the usual set of functions. So this means all the f's from x to d, where f is a function. With that interpretation, let's unpack what all of these maps are. So firstly, what does phi do? Phi takes a function from x cross c to d, function x, and it must produce for us a function from c to d cross d to the power x. Do you agree with that, Alexander?
Yep.
So now I'm going to define this function, okay? If I pick an element c of c, this function will map that c to, it must map that c to a function from x to d. Do you agree with that?
Yep.
So to specify a function from x to d, I pick an x in x, and I'll say where it maps to. Yeah. But I don't want to use the same x because I've used x as the name of my function. So I'm going to call this y. So where does y map to? Well, now I've got two parameters, c and y. And my function x acts on pairs, right? So I will just take value of x at that pair, yc. Does that make sense?
As well.
So in other words, if I've got a function from x cross c to d, I can think of it as a function from c to d to the power x. So a function from x is a two-variable function. Basically, I'm taking my two-variable function and I'm thinking of it as, so this will be my phi x, right? I'm thinking of it as a function in the second variable, where we for each second variable, we then consider the function in the first variable with that second variable being fixed. Very intuitive thing. Are you good, or should we re-explain this?
No, I'm good.
Brandon, are you also okay with this?
I am. So just one question. So this data is just a generalization of Heyting algebra, right?
Yes, yes, actually it is. Yes, if I put if my category is a lattice and product is meat, then product will be meat. And then these bijections will be just the Galois connection between the meat and the exponentiation and the implication.
Right.
So going down, that's what phi does. Going right, it's whatever we've got here. So we now expect a function from x cross c prime to d prime, and that will just take the pair x, let's call it y c. Maybe I'm going to call it c prime, and it's going to map to. So I need to first transition from c prime to c, but I can do that with my f function. Remember, f is a function from c prime to c, and g is a function from d to d prime. So I'm first going to apply f to c prime. I will get an element of c, and then I apply x. So it's x of y of f of c prime. Does this make sense, Alexander?
Yep.
Okay, so that's how I get a function here out of
wait a second. No, what is C prime here?
an arbitrary element of capital C prime.
Oh, okay, all right.
So I start with this function. Going down, it gives me this function that I've described here. So it's the function that maps C to basically the function x dash C. So where it's a function of the first variable, the second variable is fixed to be the C. Yeah? Okay, so now what about if I map this down? Now I need to do this similar transformation to this one, right? It's again the same phi here. Going down that way is the same phi. So this now should end up being a function from c prime to d prime to the power x, which should map c prime to this thing seen as a function in the first variable. So in other words, should map it to the function x dash fc prime. Yeah. Is it right? Or am I making a mistake somewhere? Because we never use G. What happened to G? Sorry, I forgot about G. There's also G here. So this is not yet, it's not good enough yet, right? Because we still have a variable here this value here is an element of D, and I want to get something in D prime. So I need to still apply G to the answer here. I want to still apply G to this. So when I transport it down here, now I've got this function of two variables, so variables y and c prime. And when I transport it down, c prime must map to this thing seen as a function of just the y variable, which will of course be this function. Here is the placeholder for the y variable. So once again, the phi, what does the phi do? So if I've got a function of two variables, what phi does to it, it views it as a function of, it maps every c in the domain to a function of the first variable, where the second variable is fixed to be that c that we picked from the domain. Brandon, are you okay?
Yes, all good.
And the last step now is to see whether it is true or not, because now we mapped all these things down this way, and that commutativity of the square to ensure, we just need to ensure that this mapping will map to that mapping by that lower arrow there. But the lower arrow there is just composing, right? If I go back here, you see it's taking my phi x and composing with f on one side and this d to the power g on the other side. So I have now an arrow from C to D to the power X, and I need to generate an arrow from C prime to D prime to the power X by composing with F on one side. And on this side, what is this function? If I have an element of D to the power X, which is a function from X to D, I will just be composing that with F. So that's actually our home functor, with X being the base, right, of generalized elements. So overall, sorry, not F, sorry, G, because we have G going from D to D prime. So overall, what will be this mapping? I start with C prime. I apply F to it. Then I apply this function to that, which will give me here the function X dash FC prime. And then I map this down here. How? This is now an element of that, right? And so how do I map it down? I map it down by composing this X function, which is a function of the Y variable here, the dash here, with the G function. So down here, it will map exactly to G of X of that thing. Does that make sense, Alexander?
Yep.
So in the end, we get that this function is mapped to the one that maps C prime to this element. But that's exactly what we've got here, mapping C prime to that element. So this maps there, and the diagram commutes. And remember, this diagram, this commutativity is the naturality of the phi transformation. Do we see that this is a bijection? Is it obvious that these things are bijections in the case of sets? How would we go backwards if I wanted to? So if I have a function from C to D to the power X, let's say function U. So it's a function of one variable, but once I evaluated that variable, then it's a function of yet another variable. Of course, this can be rewritten as a function of two variables. How? Where is X C mapped to? Well, first, compute U of C. That will be a function from X to D, and then compute the value of that function at X. Does that make sense?
Yes.
Yes.
Did you say not yet, or did you say yes, Alexander?
I said yes.
Yeah, me as well.
Okay. And it shouldn't be difficult to see that these two processes are inverses of each other. So just two ways of thinking of a function of two variables. So you got these bijections, and then you also have that they're natural in the sense we described. So that's what makes the set theoretic exponentiation to be an instance of the category theoretic one. Exponentiation is important in many categories. When a category has exponentials, it's called Cartesian closed. So Cartesian refers to this Cartesian product, and closed refers to the fact that it has the corresponding exponential. An important example of a Cartesian closed category is the category of vector spaces. In the category of vector spaces, we have exponentiation, but it is not the one that matches with the Cartesian product. It's rather the one that matches with the tensor product. That's a different story. Maybe I shouldn't have mentioned this for now. But there are other categories in which exponentiation works well. For instance, exponentiation of categories themselves, those functor categories we discussed. That also fits this picture with Cartesian product of categories. So the category of categories is Cartesian closed.
The Cartesian closed categories also are the framework for capturing intuitionistic logic.
That's right. If your category is yeah, that's one application. Another application is when your category is a pre-order or an ordered set. If your category is an ordered set and it's Cartesian closed, the first of all Cartesian product, as we said earlier, will be conjunction in the ordered set, so meet operation, and the exponentiation will be implication. So this will, if there are also coproducts, then this will be exactly a Hating algebra. So it's interesting how that arises. The bijection there reduces to an equivalence. So there is this familiar equivalence in logic that X meet Y entails Z is equivalent to, rather let me say, if and only if Y entails X implies Z. And this rule, which actually, of which actually modus ponens is a consequence, is exactly bijection of the Hom sets. It's exactly bijection of these Hom sets, where here the Hom set is either singleton or empty, depending on whether one logical statement implies the other, entails the other one or not. And so two sets which are either singleton or empty to be bijective means that one of them is a singleton if and only the other one is. In other words, this is true if and only if that is true. So this would be then exponentiation. But now this is a bit too fast. We will come back to these ideas more slowly. In fact, some of the lectures on adjunctions, this more general notion I referred to earlier, and this specific example are already online from my category theory course last year. So I will probably refer to you those lectures as far as some of these topics are concerned, but others that are not covered, they will cover here. Okay, so today's lecture was a bit of going into the depths of the Cs without being too well equipped for it. So I apologize for anyone who's listening to this lecture if at times it became overwhelmingly confusing. We'll try to unpack those confusions in the future lectures. The idea was to touch on some big ideas and also kind of give us direction to where we want to lead to eventually. We definitely want to understand coequalizers better, not just coequalizers, colimits better. So the start of this lecture gave us a good introduction to that. Another thing we want to do in the future is to understand natural transformations and their use better. So that was a good introduction to that. We did give a non-confusing formal definition of a natural transformation, but maybe we didn't give too many examples, only a few, although I think they were also simple enough. And then we briefly talked about composition of natural transformations. We will definitely come back to that later. Yoneda embedding is something we will come back separately. That part was completely confusing. I didn't say anything specific about that. And then what we did afterwards, when we talked about exponentiation, this would have been extremely confusing, but at least hopefully you saw that it nevertheless can make sense on various examples. And eventually, once we are a well-developed notion of adjunction, which is an abstraction of exponentiation for arbitrary f, when f is multiplying your C with a fixed object, then its so-called adjoint is exponentiation. But you can do this process for an arbitrary f. It gives rise to the notion of an adjunction, which in order theory corresponds to the notion of Galois connection. So once we develop the theory of adjunctions more properly, then after that, what we're doing here will become easier to understand. Great. Thank you very much.
Thank you.
Thank you.
Bye.
Bye.
Bye, everyone.